All righty. Hey, folks, how y'all doing today? So good to see you guys. All right, we are going to be getting ready to work our way through the next little bit here of calculus here. All right, we're getting ready to start our next chapter, right? So let's see here. To begin with, we talked about limits and continuity, and then we started looking at derivatives and some of their applications. Well, this next chapter, this chapter 3, deals a lot with their applications and how that relates to the graph of each of the functions. The derivatives are tied to the various parts of a function. So we're going to be looking at some different type of extrema. Now, that phrase extrema, you probably remember that from pre-calculus because we looked at relative extrema or relative maximums and relative minimums. So in calculus, we're still going to have those same kind of extrema, but we're going to give them slightly different names. Well, the relative extrema will still be there, but we're going to focus on a different type today. We're going to focus on some called absolute, or sometimes you'll hear it called global extrema. Okay. And those could be an absolute or global maximum. And sometimes they don't call them absolute maximum. Sometimes they're just called maximum. So if you just see the word maximum, that's referring to a absolute maximum. And what that is that is the highest or the greatest value on a closed interval. And that word close is a huge, huge word. We're talking about some closed interval, and it doesn't matter what those endpoints are, but they're going to be somewhere up, some x values. We'll just call them A and B to begin with here. And then we're also going to have an absolute minimum or a global minimum. And there's also times you'll just see the word minimum. This is what they're asking about. This is the least value on a closed interval. So the smallest number. So we have absolute extrema, and these are going to be essentially what we kind of play with today. In the course of our extrema, a lot of times we're going to be using the other type of extrema, which is the ones we're going to talk about here in a second. And we'll talk briefly about them, but we're going to devote most of the day to this idea of absolute extrema. So the other kind of extrema that come up, this is what we call a relative. Some people call it the phrase local extrema. Same thing. They all mean the same thing. Relative maximum. And again, you guys dealt with this on back in pre-calculus, so it's not anything new to you. A relative maximum, that's the point where your graph goes from increasing to decreasing. And I don't remember if you guys know that. Sometimes we said that this was like the top of a hill. We were looking for like the top of a hill. Now that's not what it is. It's more of the increasing to decreasing thing. And again, like I said, we'll get more into that when we get to 3.3. But it's not anything that is brand new to us. And a relative minimum, this is the point where a graph goes from decreasing, so it's kind of going downward, and then it kind of comes up to increasing. And we said last year in pre-calculus, we were going to look for essentially the bottom of valleys. And those were relative extrema. So we have two different types. We have absolute extrema and we have relative extrema. Now, relative extrema, they don't have to be on a closed interval. They can be on an open interval. But a absolute extrema always is on a closed interval. So let me draw a graph for you here, kind of so we can talk a little bit about what this is and kind of get on the same page here. All righty. Remember, now it's not a very good y-axis right there. I blame myself on that one. There we go. All right. I'm going to say this. We'll let this be A. and we'll let this be B. So on a closed interval, that means we're dealing with points that we're dealing with solid points here. So if you want to think of it in terms of, well, actually, let me draw another absolute value. There we go. So they're going to be actually on this value. They're on this A to B value. It's a closed dot. And we're just going to say, listen, there's probably more of the function going on, but we don't really care that much. We're going to close it down at these actual values. So absolute maximum, and let me see here if I can draw a graph, and we'll kind of take a look at what this looks like. Absolute and relative extrema here. Make it purple. Purple's kind of fun. All right, so let's come down here a little bit like that. Whee! Come up a little bit, kind of like that. And just for the fun of it, we'll come down here like this. Now, when we're dealing with these ideas here, let's deal with the relative first. So relative, this is when we're looking for a relative max is the top of a hill. So we try to find it. It's where that graph goes from increasing, it's going up to decreasing. So kind of like this right here. Excuse me. That is a relative maximum. And then a relative minimum, same kind of idea, where it goes from, the graph goes from decreasing to increasing. And again, we said this was like the bottom of a valley. So that kind of looks like a bottom of a valley right there. You can see why they might call it local, because compared to everything around it in its local community, it just happens to be the smallest value. So we have a relative maximum, we have a relative minimum. Those are the smallest point or greatest point to its neighboring points. Think of, again, a valley, decreasing to increasing, top of a hill, increasing to decreasing. Now, when we write a relative maximum, and this is actually a big deal here, when we write a relative maximum, we're always going to write it in such a way that it will be a point. A relative max or a relative min is always going to be written as some x, y point. We always write it as a point. It's a location. So a relative extrema is a location. Absolute extrema is a value. And so when we look at absolute extrema, we don't write it as a point. We write it as a function value. The College Board will dock you if you write these differently. Okay? So we're going to write absolute extrema as a function value, or relative extrema we'll write as a point, some x and y. So on absolute extrema, we're looking for where is, on that closed interval, where is the largest value and the smallest value. So let's see if we can't draw those up there. If you notice, this relative maximum, that is the greatest value on a graph. All right, so if I think about it here in terms of, let's see, what color can I use? Try this one. If I think of it in terms of drawing like a horizontal line to kind of capture it here, you can kind of see how that is the exact top of my graph. There's nothing larger than it. It doesn't go any higher. All right, so this would be an absolute maximum. So an absolute maximum and a relative maximum can be the same place. Just like an absolute minimum and a relative minimum could be the same location as well. In this case, though, it's not, and we'll see that here. If I'm looking for the smallest value, it looks like I have my smallest value right here. So nothing gets smaller than that point, that endpoint. So then I would say, okay, well, that looks like then the smallest value right there. That would be my absolute minimum. So absolute maximum, that's a function value. Absolute minimum, that is also a function value. Now we can have that greatest value, the maximum value, or the smallest value, the minimum value. We can have those occur at more than one location. And we'll take a look at an example of what that looks like here in a little bit. Relative extrema, relative maximum, relative minimum, graphs can have multiple of them. It's just anytime the graph changes direction, you're going to have either a relative max or a relative min. So we can have multiple of those as well. Remember, for absolute extrema, we always write it as a function value. And relative extrema, we write as a point. Absolute extrema are always going to be on some closed interval. Relative extrema, they don't have to be on a closed interval. It can go from a negative infinity to positive infinity. They can go the entire gamut. So we have these ideas of extrema, and I'm hoping this kind of starting to get the language a little bit, because today's going to be a lot about language. Okay. So absolute extrema, relative extrema. So now let's just add a little bit more language to this here. And we're going to talk about something called critical number. A critical number. These are x values where there are either horizontal tangent lines So this, in a horizontal tangent line, remember that's a horizontal line, that's a flat line. So that's where our derivative is equal to 0, because that's the slope of a horizontal line. Or it could be located, at x values where the first derivative is undefined. That could happen at a cusp, or it could happen at places where there would be a vertical tangent line. So we could probably do that where f prime of x, we could probably do this a little bit better here. It's not really about tangent lines, it's about the values. Those are horizontal tangent lines. So, in other words, anytime I have a derivative that equals 0, or a derivative that has a vertical tangent line, and I'm going to show you a couple of graphs of these so you can kind of see these a little bit. We call that a critical number. Now, the reason why critical numbers are important is because for relative extrema, they only occur at critical numbers. And again, we're not going to get too much into the detail on relative extrema. We're going to save that for a couple days. So we'll save that for next week. But relative extrema, they only occur at critical numbers. In other words, if you notice here, you can kind of see it here with this blue line that we have here. At this location, and we'll call that, it doesn't really matter, we'll call it D. At that location, because that is a horizontal tangent line, that's where the derivative has a value of 0. And if you notice, we had another one of these on here, another relative extrema. And so this, we'll call that C just for the fun of it. So at this value right here, this is where that derivative is equal to 0. So critical numbers, and we call them critical numbers because it's literally that. Something critical happens there. When our derivative is 0, or it might be undefined, or in some way. And again, that's what we're going to look at. And we're going to get to how critical numbers relate to absolute maximum, absolute minimum in just about 1 minute here. But to begin with, let's throw a graph up there. So you're going, where are all the practice problems, Williams? Yeah, today's a big language day. We're going to try to speak the language here correctly and be able to speak the same stuff together. So let's see if I can't draw ourselves a graph, and we're going to see some critical numbers. Alrighty, let's see here. And I'm sure you guys are going to draw this on your graph paper here, so yours is going to be a little bit nicer than mine. All right, let's draw a few lines out here. And let's see here, we're going to draw a few lines over here. Let's graph some points just for the fun. I want to put a point right here. That's a good spot for one. Whoop, like that. And let's put one right here. Whoop. And let's see here. Let's put one right here. Like that. And we'll put one right here. And let's see here. We'll go out here and we'll put one. And we'll put one. Ooh, let's go right here. And then we'll go down here. Now let me play connect the dots here just a little bit here. I'm going to come up here, a little graph. Ooh. And we're going to maybe flatten this graph out here. And again, friends, the graph I'm drawing here, it's not a function. I mean, it's a function, but I made it up, so don't think too much about it. See if you can figure out where the critical numbers are. Okay, what x values give us critical numbers, and what makes them critical numbers. So go ahead and pause the graph, or pause the video, and see if you can figure out where the critical numbers are and what makes them a critical number. All right, let's see how you guys did. So critical number right here. And I should be moving that down just a little bit, right about there. All right, and that's a critical number because this is where our derivative is equal to 0. So anytime we have a horizontal tangent line, that's where a derivative equals 0. So notice, we got a horizontal tangent line right here. And actually, I got one as well right here in the middle. Now notice, even though there's a horizontal tangent line, it's not a relative extrema. But again, critical numbers just means something happens there. So something happens at these values. We don't necessarily know what, per se. We will in the coming days. We just know something happens there. So f prime of -3, that equals 0. That means something critical happens there. F of 1 right here, f prime of 1, that would have been equal to 0. Because again, it has a horizontal tangent line. And we have f prime of 3 equal to 0. Horizontal tangent lines. And let's see. Well, it turns out I got a vertical tangent line too. I hope you saw it. Be right about here. See if I can't make it a little bit more. We got a vertical tangent line. So that is where the graph is undefined because of that vertical tangent line. So f prime of 4, we'd say that is undefined. Still a critical number. Something happened there. And as as we go through this chapter 3, we will talk about what happened there. And lastly, we have one more critical number. And there's no vertical tangent line here or any of that kind of stuff. This is just a cusp. If you notice, we have a really sharp negative slope coming down here. I mean, you can kind of see. And then we got a little bit more gradual positive slope here, but this is a cusp, this sharp turn. So at this cusp, and again, we wouldn't say that it's a critical number because it's a cusp. We'd say it's a critical number because the value is undefined. Well, why don't you do me a favor? Let's try one more thing here. What I want you guys to do, go and take a second here. You're going to pause the video, and I want you to tell me where the relative maximum are. You don't have to tell me why yet. We'll save that for later. And where the relative minimum are. Remember what we said about a relative max. This is where our graph goes from increasing to decreasing. Relative minimum is where we go from decreasing to increasing. See if you guys can determine where those positions would be. Go ahead and pause the video and we'll see. All right, so here we go. Let's see how you did. This right here, this is going to be a relative extrema. I'm going to point arrows at all of them here, and then we'll talk about what type they are. Now, funny thing is, there's only 3 relative extrema. So just because we have more critical numbers, we had 5 critical numbers, but only 3 of them gave us a relative extrema. So the point -3, 4 there, that was a relative max. Because it went from increasing to decreasing. From -1 at -1, 2, that would be a relative minimum because our graph goes from decreasing to increasing. And again, this is a review of what we did in pre-calculus, so this isn't necessarily anything terribly new. And then our graph here goes from increasing to decreasing at the point 3,3. That's also a relative maximum. Let's try one more thing here, friends. Can you tell me where the absolute maximum are? And can you tell me where the absolute minimum is? Let's go ahead and pause the video and see if you can tell me where those are located. All right, let's see how you guys did. I'm going to draw an arrow to where the relative max or the absolute maximum is. This is the highest point right here on our entire function. And notice the absolute minimum might be right here. So the absolute maximum, and remember as well, we write this as a function value. This occurs at f of, what was that, -3 equals 4. So the relative maximum and the absolute maximum, they ended up being located at the same area, but you notice they're written differently. One's a point, absolute is a value. The absolute minimum, that's located over here at one of these endpoints. It's not a relative extrema, even though it went decreasing. Notice how these endpoints aren't relative extrema because it went from decreasing, but it never went to increasing. We don't know what happened there. This was increasing over here, but we don't know what happened over here. So we don't see it turn, which is why they aren't relative. And guys, this leads us to a very, very big theorem. Okay? A very big theorem. Here's what the theorem says. And again, there's 3 abbreviations we can use in calculus. This isn't one I would recommend you use. The other 2, fine. I don't use this one myself. I know some people that do. I wouldn't. I'd go ahead and write it out, even on the AP test, because it doesn't take long when you use this one. Even if you say extreme value theorem, I'd go ahead and actually write out what it is. So the extreme value theorem, here's what it says. It says if a function f of x is continuous on the closed interval from a to b. So we're talking about closed intervals here. Then the extreme values, in other words, the absolute max and the absolute min, then the closed interval, sorry, will have both extreme values. So if it's a closed, if it is a closed interval, it has to have an absolute max and an absolute min. Now, a little corollary to this, a corollary is an offshoot, really closely related to it, is this. Absolute extrema are located at the critical numbers of a function and or at the endpoints of the critical closed interval. We can kind of see it here on our own little problem that we have going on here. Our absolute extrema have to be located at any of these little critical numbers because something critical happens there, or it can be located at the endpoints. In this case, at when x is -4 or x is 6. So every closed interval, you're going to have a largest value and a smallest value. Yeah, largest value and a smallest value. And that's what we're going to be playing with for the rest of the time. We're going to be playing with this idea of extrema. And I'm just going to apologize. I'm going to be singing here in a little bit. All right, I'm going to channel my inner Sarah. I can't say her last name, Barceus or whatever. I heard the song on the radio and it just seemed like calculus to me. So you have to apologize for that. Anyways, here we go. So given a function, I'm going to write it here in a second. So give myself a little space here. Determine the absolute extrema from the closed interval from -2 to 4. So I'm giving you guys a closed interval. All right, now here's the function I'm going to give you. I don't want green, I want black. So f of x equals 2x cubed. That's not a 2. 2x cubed minus 3x squared. We have minus 12x. Hard to read my own handwriting sometimes. Plus 1. Now, friends, it's easy to kind of jump right on into doing these things, but there's a process because here in calculus, especially on the AP test, we have to explain everything we do. So, I got her name right. She has a song called Brave, right? And it said, she goes, say what you wanna be or wanna say, right? I'll sing it in a second, just so y'all can laugh and have a good chuckle. All right, so she's got this song. Say what you wanna say and let the words fall out. And honestly, I wanna see you be brave. All right, so you got that song. Well, for us, anytime we're dealing with extrema, we're going to be doing something a little bit different. We're going to say what we're going to do, then we are going to do the work. And when we're done, we're going to say what we found. So, all right, get ready. We're going to sing this a lot here, especially in class. I'm not going to sing it on the internet, but I will sing it right now. So we're going to, it's three things here, friends. We're always going to start off. We're going to say what we're going to do. And then we're going to do the work. And when we're done, we're going to say what we found. All right, so say what we're going to do, and then we do the work. And when we're done, we're going to say what we found. And we're just going to do it over and over and over again, right? So that's essentially, whether it's absolute extrema or other things that we take a look at, whenever we are on the AP test, we're going to do this little three-step process. Yep. And it's going to happen. You're going to think, my gosh, this takes forever. Yeah, it can. All right, you'll get quicker at it. So the first thing, we're looking for absolute extrema. So we know that absolute extrema can exist when our derivative is 0, critical numbers, or undefined, right? And it can also exist at the endpoint. So we're going to say what we're going to do, all right? Absolute extrema can exist when f prime of x equals 0, f prime of x is undefined, or when x equals -2 or 4. Okay, and it's going to seem pretty redundant as we go through this. But what we're doing here is we're giving ourselves permission now to go ahead and do math. We can't just hop in and do it. We got to give ourselves permission to do what we want to do. So the first thing I'm doing is I'm talking about derivatives. So what that allows me to do then is it allows me to go ahead and take a derivative. So I can't take a derivative until I've given myself permission to take a derivative. So we say what we're going to do, and now we're going to do the work. So I'm telling myself here I am playing with derivatives. So I'm going through, I'm doing my power rules here. And if you notice here, a lot of this I'm dealing with, I notice I'm dealing also with it being equal to 0, right? So now I'm giving myself permission to set my derivative equal to 0 to actually solve this thing. So I say what I'm going to do, and now I'm doing the work. And you can already probably hear it in your head. And when I'm done, I'm going to say what I found. Now, usually it's at this time in class, you guys are like, whatever. And then after like 2 or 3 days, I usually get a handful of you guys, you'll sing it with me every single time. But we don't really have that luxury right now. All right, so we have our critical numbers when x equals 2 and x equals -1. Notice this is a polynomial, so there are no undefined derivatives. But now I know where the values are located. The critical numbers, or I'm sorry, the absolute extrema, they would have to be at either one of these two critical numbers or my two endpoints. So that means they'd have to be located when x is -2. They have to be located when x is -1. So where my critical numbers are, or where my endpoints are. That's where the largest value is going to be located for my absolute extrema. Just like that. So, friends, once you're here, not too big a stretch of the imagination. We're literally going to go back and we're going to plug all our values in for here. So you're going to plug them all in there. And when you do plug them in, all right, I'm going to go ahead and assume you did a little bit of algebra 1, or maybe you use your calculator. I don't really care. But when you plug in -2, you're going to get -3. When you plug -1 in, and I'll show one just so when you're at home and you're trying to figure out what I'm doing, we're literally going back to the original function, and we're plugging these values in. Every once in a while, I find somebody when you first start doing this, you plug it back into the derivative. We're not looking for the maximum min values of the derivative. We're looking for the maximum min values of our function. So we plug them in. So there's 8. This is negative 19. And we get 33. So from here, we're looking for the smallest value, and we're looking for the largest value. There you go. Here's our smallest value, and here's our largest value. So this is going to be our absolute min. And this isn't how we write it, by the way. I'll show you that in about 1 second. This will be our absolute max, because I know that they have, by the extreme value theorem, they have to be located at an endpoint or a critical number. So we say what we're going to do, and then we do the work. And now we're at the end, and when we're done, we gotta say what we found. So here we go. The absolute maximum, or minimum, let's write that out, is, and we don't have to say where it's okay, we just can just go right on into it. The absolute minimum is f of 2 equals, notice I'm writing it as a function value. The absolute maximum is f of 4 equals 33. Now later on, as we get to some of these, there actually is more that would go into our reasoning, but for this one, it's not that. So what do? We said what we're going to do, and then we did all our work, and when we're done, we say what we found. Okay, and we're going to essentially do that time and time and time and time again. Okay, so what we're going to do right now is we're going to play with this a little bit. I want to make sure that we're going to do a few of these together. Oh, wrong thing. Get out of there. There we go. All right. So this time I'm going to give you a closed interval from -4 to 3. And the function I'm going to give you, let's try f of x equals x cubed plus 3x squared. Oh, minus 9x minus 2. All right, friends, so this is what you're going to play with here. So go and pause the video, see if you guys can go back through, make sure you explain what you do along the way, and see if you can figure out the absolute extrema. All right, let's see how you did. Hopefully, pause it up now. So the first thing we're going to do, friends, is we are going to say what we're going to do. All right, and I got a feeling you probably just copy and pasted what we did before, because honestly, I hate to say it, but you can do that. So, oopsies. I was about to write say again. Absolute extrema for f of x can exist. Note that word can is very important. Can exist when f of x, f prime of x, sorry, equals 0, f prime of x is undefined, or when x equals -4, or x equals 3. I gave myself permission to deal with derivatives. I gave myself permission to set the derivative equal to 0. I've given myself permission then to test those values. So we say what we're going to do, and then do the work. Now this is the actual math part, the actual calculus part. And if you notice, there's really not much to the calculus part here, because once you do your derivatives, you're done. With calculus, after that, it's all algebra from there. You can tell why they used to call, notice I'm not setting my derivative equal to 0 first. Notice I'm always setting it equal to f prime of x first, and then I set it equal to 0. Big thing. Don't miss that. Don't rush it. Don't combine the two steps. You will lose points. But you can see why they call it advanced algebra. There's really not a lot of calculus involved. It's really algebra. All right, so we're going to x plus 3, x minus 1. So x equals negative 3, and x equals 1. So we're going to plug in our values now into our function. So we're going to plug them all back into the original function. And again, I'm going to write it again so I don't want there to be any confusion. It's going back into the original function. And that would be when I plug that one, and I'm going to get 18. All right, so and then I have what? F of negative 3 here. So I'm dealing my critical numbers now. When I plug this one in, I get 25. Oh, there's a larger value. Then I plug in my F of 1. I get a negative 7. And let's see, when I plug in my F of 3, I'm going to get 25. So again, just to see what we found here, this right here, there's my absolute min. And right now, for some of you guys, it might be a little bit like, okay, I did this, but I'm really struggling with something, right? Because what's the absolute max? Well, it turns out if they're the same thing, remember I said it has to have at least one. That just means there's one y value. That y value, that could happen at different places. I mean, it doesn't have to happen at just one. It can happen at both. Turns out, friends, they both are. We'll write it as one, but they both are. So we said what we're going to do. We did all the work. And when we're done, we're going to say what we found. So that absolute minimum is f of 1. That was our smallest value, equals negative 7. The absolute maximum is f of negative 3 equals, watch this, f of 3. I had it happen twice, so I get to the value. Happened twice, so I need to make sure I include it both. So we say what we're going to do, and then we do the work. And when we're done, we're gonna say what we found. All right, so we have it all now. All right, hopefully we're starting to get the idea a little bit, at least a little bit, right? Yeah, pause it, I'm about to erase it. If you need to write something down. Let's try it one more time, friends. One more time. I mean, it's fun to do with polynomials, but it doesn't have to be a polynomial. We're just doing polynomials right now because it's a little bit easier. What about if we get something like, ooh, how about this? This will be fun. This is the extreme value theorem, friends. It's a biggie. It's a biggie. So we got introduced to critical numbers today. We got introduced to relative extrema. We spent majority of the time playing with absolute extrema and playing with the extreme value theorem. All right, go and pause the video here and see what you guys can do with that. Oh, hopefully you're still watching, because I maybe made a mistake. There we go. I didn't give you a new domain. Probably need to do that real quick. I'm struggling here. There we are. Let me give you a new domain real quick. How about that? Then we'll go and pause the video. Then I'll give you a little time. Let's see here. That's called cheating. Get rid of it. All right. I'd like you to have your domain go from 0. Let's go from 0 to 3 pi over 4. All right, now go ahead and pause the video and finish it up. Sorry about that. All right, here we go. You guys, seriously, the explanation part, that is always a point on the AP test. So write it down. So we're going to say what we're going to do. Here we go. Absolute extrema can exist when f prime of x equals 0, f prime of x is undefined, or when x equals 0, or when x equals, and I'm going to have to write that one in there. So we say what we're going to do. And now, friends, hopefully you did the work. All right, I told you we're always going to have there's going to always be a little bit of trig stuff here. So f prime of x equals, the derivative of 1 is 0, but be careful here now, minus, realize I'm going to be doing a chain rule here. Hopefully you guys made sure to do your chain rule. That's the sound of the man. There's my outside function. Who's working on the chain gang? All right, here we go. And the inside function. You can kind of see your outside function and your inside function a little bit there. So the derivative of cosine, well, that's going to be negative sine. That's the outside part. And then the derivative of 2x is just 2. So when we clean it all up and set it equal to 0, I end up with 0. Negative times a negative is a positive times 2. I get 0 times 2 sine of 2x. So we solve it then. We have 0 equals sine x. And we're trying to remember, when does sine equal 0? So just think about when sine equals 0. You need to go back. Again, you guys have been doing those unit circle quizzes, so hopefully you have this down. When sine equals 0, when y equals 0. So that could be at anywhere on the x-axis. So that could happen at 0. So my angle could be 0. It could happen at pi. Could have happened at 2 pi. So when I plug them in here, so my angle, notice my angle is, be careful on that as well. That's our 2x here. So 0 equals 2x equals the angle. Pi equals 2x. And 2 pi equals 2x. So we're just solving a real basic trig equation. So 0 equals x. And I only put these values up there because I'm only going to be using values that fall in my domain. And I got pi equals x. I saw it. And I can stop there because I can already see that pi is already out of 0, 3 pi. So I have my endpoints, f of 0. So I'm going to be plugging that in there. So again, I'm going to always write the first one just so you guys can see it yourself. Don't worry about ever writing them if you don't want to. You definitely do not need to. Okay. And then I have f of 3 pi over 4. Since it is trig, I'm going to go ahead and write them out here. Now, I told you guys on some of the other stuff you don't have to simplify. You always have to simplify trig values. If you don't simplify trig values, you will get dinged on the AP test. And notice I only got one other of my critical numbers that falls in between my domain. That's pi over 2. So I'm going to add that in here. So 1 minus cosine of 2 times pi over 2. All right, yeah, 1 minus cosine of 0. So that's 1 minus 1, which is 0 there. Let's see here. I got 1 minus cosine of pi. Cosine of pi is -1, so I have 1 minus a -1. That would be 2. And we get our last one here. We have 1 minus cosine of 3 pi over 2. So 1 minus 0 is 1. So we said what we're going to do. We did the work. And when we're done, we got to say what we found. All right, well, let's see if we can do that then. The absolute maximum, or minimum, let's do that first, is f of 0 equals 0. The absolute maximum is, and I'm going to have to go through and write that one, equals 2. And that was at pi over 2. All right, so, and again, what do we do, friends? We said what we're gonna do, and then we do the work. When we're done, we're gonna say what we found. You're like, please stop singing, Williams. I know I can't help it, friends. But all right, that's enough for today. I'll see you guys in the morning, and we'll talk more about it.